In this recording, we're going to review some of the things you learned in Algebra 1 about exponential growth and decay. So let's start out with a simple money example. A lot of our examples we use involve money because it does grow exponentially, interest. So in this case, you're going to read through this problem and underline the important stuff. So we've got a 5% interest rate, which is ridiculous because you'll never see that in a bank, in a savings account. But let's just play money here, right? And you're going to deposit $400 into that account. And let's just see how it comes out. So if you had 5% of that $400, what would that increase over the course of the year? And so that's pretty simple. Turning 5%, you always want to think about that in terms of a decimal. That would be 0.05. And that's a huge source of error. Being really careful. That's 5 per 100. 1/100th place. So the 5 needs to be in the 100th place. So we're just going to do a 0.05 times what we call the principal. The principal means not like the principal of the school, but the principal is the initial investment. And so you just do that multiplication. That means you get $20, right? $20 was earned. How much it increases. Over in Part B, it says, okay, so how much would you have at the end of the year? You had $400. Without doing any extra work, you got $20 just for your money sitting in that bank. So you add those two, the 400 and the 20, and you have 420. Okay? So by what single number could you have multiplied? Essentially doing steps A and B in one. Well, I guess what we had was 400 plus 400 times 0.05, right? So this is like one of these, and this is like 0.05 of these. So altogether, wouldn't it be like having 400 times 1.05? All right, essentially factoring out a 400. So essentially, what we can do is multiply that base, that growth rate of 1.05. Remember, if it's a 1 that we're multiplying by, the 400 doesn't change. If it's less than 1, the 400 decays. It exponentially decreases. So in this case, if we wanted 2 years and 10 years, we could figure out how much we would have at those amounts of time and round to the nearest cent. So pause the recording and play it when you're ready. Okay, so hopefully for 2 years, you realized we would take $400 and do 1.05 twice. So that's going to give us the amount of $441. Similarly, for 10 years, $400, we'd have that growth rate of 1.05 10 times, right? It's going to compound. And if you do the math there, it's $651.56. So now let's generalize. If we want to do a function, s, not crazy about the variable s, kind of looks like a 5. We'll try to make it curly like that. S of t. What would that be after t amount of years? So we're going to start with our initial amount, and we're going to have our growth rate of 1.05. And just like we did to the second and to the 10th power, we're going to raise it to the t power. Okay. So finally it says, all right, look on your table, on your calculator, for how long it will take for the initial investment of $400 to double. Okay. So let's put this function into your calculator if you have one, and then look in your table and find out when the $400 would double. Play the recording when you're ready. Okay, so I'll just go through the calculator steps, and you can watch or you can confirm what you already had. So if we're in our y equals, enter that function. Okay, so we're interested in the money doubling, so that'd be $800. It looks like it's closest to being 14 years. So we can say it's from the table. S of 14 is around 791, whereas S of 15, if I recall, that worked out to be around 832. I guess I should call these 2's, right? Alright, so this is going to be our general model here for exponential growth. It's going to be 1 plus the percentage rate raised to the t power. So why don't you take a moment to try to work out exercise 2. If you don't have your own graphing calculator, remember you can use the Desmos graphing calculator. You can go to desmos.com and access their graphing calculator. Okay, so in this example we've got $250, 3% per year. Work that one out. Okay, so it looks like choice 2. Alright, this is going to be a little tricky. When we are decreasing, we're decreasing from a base of 100%. If we were multiplying by 1, that would keep everything the same, but if we multiply by something less than 1, or less than 100%, that's going to decay it. So we're saying here, if you want to decrease by the percent listed, the base you're going to multiply by would be 0.09. Excuse me, be 0.9, or 90%, right? If we had 2%, you're subtracting from 100, etc. Okay, and if I have 0.5%, I really have to think about that one carefully. That's less than 1%. So if I subtract 100 minus 0.5%, it's actually going to be 0.995. Now I always like to write this leading zero here because if I just have like 0.995, sometimes that little dot gets lost and it's hard to tell. Is that 995 or point? So put in that leading zero for clarification. Okay, and finally, I'd like you to work on this example here where we have a decreasing exponential model. We're decreasing by 4% per year. Started with 12,500 residents. And I want to know, all right, in 10 years, how many will we have? So go ahead and work that out and play the recording when you're ready. Okay, so we should have 12,500. We're decreasing. So that means our rate, our base is 0.96. We're going to do that to the 10th power. And when you do that work, you're going to get around 8,300, choice 4. Thanks for watching.